Me and my colleague Ivan Masar, we're going to present today TTTech triggered Ethernet. Whoever has had any issues printing their documents, I'm sure they had some network issue. We're kind of trying to fix a little bit of that here. Um, so all of you guys have created some wonderful end systems, some software development. Now, what do we do with that? We need to connect them to each other. We need to make sure that everything responds in a timely fashion. We need to make sure it's fault tolerant, and we need to make sure it's safety critical. All of that while being in space, and there's nobody to press the reset button, or the reset button might be outside where it's not nice to go. Um, so why TTT Ethernet? So TTT Ethernet is optimized for three things mainly: to being deterministic. I've developed some control systems when I started in working in aerospace in 2010, and one of the reasons why we didn't use AI or neural networks is because it's not deterministic. You got a set of inputs, and you're not sure you're going to get the same thing out the next time. So being deterministic is very key and very important. Now AI and neural networks have advanced so much that you can make them a little more deterministic, but we're not there yet. Fault tolerance. So what do we do if something fails? Same with software. I used NPSS for several years. It's a NASA product. It failed, and then I didn't know what was wrong with it. It just said something went wrong and kicked me out, and I had to start my whole analysis again. At least being able to isolate what the problem is. If there's a problem, be able to continue functioning or partially functioning, to be able to isolate the issue and continue your operation. And safety critical. There's a quote that some of our teammates said. There's two types of safety critical: the one where your wife is going to fly in, and the other one where your mother-in-law is going to fly in. It depends which one you choose. So you want to make sure you're safety critical and everybody gets their safety. Everybody gets to do what they need to do. You don't want a bunch of junk just flying around and causing some issues, not only to other humans, but to themselves or to other operations. So provide fault tolerant networks, timing to all application. All your end systems will be in our network are synchronized. At least there's different levels of synchronizations. You can be synchronized at the application level, or you can be synchronized at the network level. Depending on what your needs are, being synchronized at the network level provides a lot of benefits. You know when things are supposed to leave. You know when things are supposed to arrive. For those who do control systems, your control loops are more stable when you know when things go out and when things come back. Provide synchronous and asynchronous deterministic Ethernet traffic. Not everything needs to be controlled. Not everything needs to be timed. If I send an email, it doesn't need to, if it takes one more minute, I think I'll be fine. However, for other type of network like a rate constraint, we had a good example yesterday where they tried to send, I think it was 12 cameras type of network at the same time. And yeah, there was a bandwidth that you could use, but when you do it all at the same time, things start to fail. And when things start to fail, then you have to send a log that says, okay, this failed. And at the same time, you have to report to the, I don't know, to the FCC or to the flight computer, this also failed. And the whole bandwidth in the network crashes. So it's important to kind of have visualization of what your network looks like. It's like, I guess, LA traffic at 5 p.m. Everybody's trying to get home. And provide 802.3 Ethernet support, best effort. Again, all of this is done in the same wire, in the same card. So there's items that you don't need to be time triggered or rate constrained, but you also want to connect. Not everything needs to be time triggered. You want to connect a regular laptop to your network. It doesn't need to have anything special. You just want to connect, know the status of how things are working. You want to be able to know what's going on your system. That's not time critical. You can connect an iPad or whatever other end system that you have on time. So all, like I said, all traffic classes run on the same physical wire. This reduces the amount of weight and also the amount of cost you have to deal with. Provides redundancy management for Ethernet networks on different topologies. Like we all know, we have different type of channels, channel A, channel B, channel C. You can choose which one to redirect. If one fails, you can redirect to a different way. Um, most of my career has been in aerospace. There's this time where 3 hydraulic networks were powered through the same area. There was a failure, and all 3 were chopped at the same time. So please make sure you don't put all your wires in the same place. You kind of put them separate around so all the channels are able to get to their destination, if not one way, another way. So the next slide is a little bit of quality of service. Just like I mentioned, at the very right side of you have your time triggered. You know when the time is gonna leave. You know when the time is gonna arrive. If it doesn't arrive on time, that means something went wrong. If it arrives too early, maybe there was some issue with the end system. If it arrives too late, maybe it was compromised. You no longer need that information, so it gets dropped. That's part of the fault tolerance. You gotta make sure you're on time all the time. The next, you have your AFDX or rate constraint. You have a certain amount of bandwidth. You want to make sure that everything you send out at a certain time is able to get to their destination, but you don't know, you're not sure when you're going to send it. You have a fault, you have something that you want to make sure it has the right bandwidth to get there, but you don't know when it's going to be there. So asynchronous sometimes can even be longer than time triggered, or it can actually be faster, but it's not guaranteed. And then you have your regular IEEE 802.3 Ethernet, best effort Ethernet, where you kind of, okay, it takes 1 minute, fine, maybe it gets dropped. I get a message that it got dropped. It'll get there eventually at some time. My printer might work next time. So that's a little bit of the basics of TTE Ethernet. I hope I kind of set the level, and then my colleague, Ivan Maser, will continue a little bit more about the specifics on space and where it's being used.
Thank you, and also welcome from my side. So I will introduce some of the, let's say, products we have currently in the development supporting the TTE Ethernet technology, and also what's on our roadmap. So how this all started. So after the TTE Ethernet technology has been developed, so the first component we have developed at TTTech to implement this functionality was a TTE Ethernet controller. So actually, this was a project which was also or is contributing to the development of the new European Ariane 6 launcher, because this time-triggered Ethernet controller has been selected as a main communication controller. So the whole Ariane 6 network is using TTE Ethernet communication. Then based on this basic component, we started to develop the board-level products, and those are currently in qualification stage, I would say, and will be used on the gateway as let's say, the main component used to implement TTE Ethernet functionality. And based on the single board products, we also continue to integrate some of the functionality into, let's say, the whole modules or boxes. So integrating the boards for the communication over TTE Ethernet with additional modules like power units, onboard computers, mass memory units, maybe other units also as well in the future. So to provide complex avionics solutions. So let's start with the explanation how TTE Ethernet, so the functionality of this communication protocol, which has been explained a little bit, is implemented in the TTE controller. So basically, to implement any network, and therefore also TTE Ethernet network, which is based on Ethernet, we need 2 types of components. We need the network interface devices, so which allows the CPU to communicate with the network, and then the switches. Oh, it was a bit too fast. And then the switches that just route the traffic from between different systems. The TTE controller we have developed actually fulfills the both functionalities or can be used in both use cases. So as you can see on the picture, it includes some main TTE Ethernet IPs. One is the end system, then on the other hand there is a switch, and also some additional units, so including the Leon 2 CPU, which is used for the management purposes, several interfaces, memory controller. So basically it's a really quite a complex system on the chip, which allows us to build both type of devices to be included in the network, so end system and switches. The chip is, I don't know which is this timer here, but just jumps to the next slide. So just to explain how the chip is used in both use cases. In the end system use case, the end system just is able to send the traffic into the networks according to some schedule. So time triggered means basically that the traffic is scheduled. So for this, we need, again, two functionalities to be fulfilled here. One is to know in the whole network what is the schedule of the traffic. So it means at which time point I need to send the data packages, at which time I will receive some data packages. And of course, the global notion of the time. So all the systems in the network needs to have the same notion of the time to be able to synchronize to this traffic. So in the end system use case, there are three interfaces available as so-called host interfaces. So if you have a space processor, then you can connect it to the chip to send and receive the data then from this network interface controller, either through PCI or quote SPI interface or SPI or space wire. And then in the switch use case, and on the Ethernet interface in the end system use case, there are 3 channels because we said already. So in the space, it's often used as a dual fault tolerant network, so meaning 3 network channels. And in the switch use case, there are actually implementation using also dual core lock steps. So you can see on the bottom side of the chip 2 switch IPs that are connected in this dual core lock step. So meaning the switch process the frames, the data in 2 cores, and before the data are sent out into the network, they are compared. So basically this allows us to build or to use the switches to build some fault containment regions in the network, meaning so no faulty data, which could be caused, for example, by some SE effects, will be not sent into the network. So this failure will be not propagated further into the network, but will be, let's say, limited on the output of the switch. So I hope last time. So the switch has been developed as a rad-hard design, so meaning there are some design measures implemented, and also the manufacturing process of this used to produce this chip is rad-hard. So the chip implements several protection mechanisms, including the memory protection, scrapping of the memory. So all the memories are automatically scrapped. So there are some information, and of course the single bit failures are corrected, double bit error or multi-bit errors are detected. There are also some additional mechanisms implemented, let's say, using different type of failure counters included in the chip. So there is possible to really detect in a very detailed way what reason was, for example, for the dropping of the frames. Was it some kind of failure in the data frames? Was it maybe some wrong timing? So this provides a lot of status monitoring capabilities of the device. So, and this status can be then provided and can be used to detect if there are some failures in the network. And the process which has been used to manufacture this chip, it's a 65 nanometer rad-hard process at ST Microelectronics. So the chip is produced in Europe, in France. So it's also, let's say, the process which already use a lot of, let's say, the specific logic cells that are hardened against the radiation. And in addition to this, most critical part of design have been implemented using the triplicated registers, or TMR logic. So this was the chip so itself. Maybe one last comment also to this. So you have seen there is also the CPU integrated into the in the chip. So this, let's say, extend the capabilities of this device significantly, because this CPU can, on the CPU, a different type of code can be run. So ranging from management purposes, so monitoring, observing the status device, providing this status over the network to some kind of upper level control system. It can be used to send, receive the data, also interact with other devices that can be connected to the chip using some of the additional interfaces available. So the flexibility of what can be done with this is quite a let's say broad range of application that can be implemented here. So in the basic two units, then using this chip for communication in TTE Ethernet networks are TTE Ethernet end system, so which is shown here. So it's in the 3U compact PCI form factor boards. There can be produced, or they are available in two different quality grades for the lab development using the classic parts. For the deep space missions, like on the Lunar Gateway, using class R components. And here what we see also is how the software stack is implemented on such device. So basically, there are the drivers available for real-time operating system ranging from VxWorks, SpikeOS, also some other supported, and then can be used then to transfer the data from the board to the host CPU, and also to provide the synchronization of the applications running on the host CPU. So basically, this is also one of the important features of the TTE, not only to transfer the traffic according to defined schedule, but also the capability to synchronize the applications running on different CPUs using the network time. So also yesterday there were some talks let's say dealing with the synchronization of the application, and especially if we speak about a very complex system like the gateway is, because it consists of a lot of processors running in several modules connected to each other, then always is let's say the task of how to synchronize the execution on different type of applications running on different platforms, on different processors. And one of the methods, and this is something what synchronized distributed system running on the TTE Ethernet network provides, is to really synchronize the execution times to the network. So basically with the communication. So this also leads to the optimal usage of the resources that are available in the system, because all applications just run when the data are there. They know when to send the data. There are no times where the processor is doing nothing. So basically the synchronization of such application then to the data flow provides the best, let's say, option how to execute the code or the application in a distributed complex real-time system. So the second type of device I have mentioned, which we can implement using this TTE Ethernet controller, is a TTE switch. So basically, it interconnects the devices connected in the network. And as I already mentioned, it provides also some, let's say, capabilities running or functions that are implementing using the code running on the internal CPU, used for health data monitoring, meaning built-in system tests are running all the time or at the startup of the device and provides the communication status of the device, but also the capability to configure the device through the network. So if you imagine if you have a very complex network, very complex spacecraft, and you want to configure it for the new use case, then it would be quite difficult to run with some kind of programming device. So therefore, all the devices can be configured through the network from one station, and also the new firmware can be uploaded using the network. So using the SNMP typically or TFTP protocols. As I already mentioned, one of the important features is how to synchronize the applications of why to use this time synchronized network in such complex spacecraft. So basically, as was already explained also by my colleague, it's always, let's say, the advantage if you have time synchronized system, especially complex one, for different reasons. For example, if you do the continuous integration of the system, so not all systems are available at the beginning. So you want to add some system into the network, so for some reason you need to remove them. Then you want to test them to integrate. Here to have the synchronized distributed system is really beneficial, because if you add one new device into the network, you will not influence the remaining traffic. Of course, if you are using time-triggered traffic. So it means you can step by step integrate different devices, test it, integrate, verify if everything is working properly, and then you can still have this opportunity, let's say, to add new devices, or just a very easy example from Gateway. If the modules of the spacecraft are connected, like there is a dock device transporting the astronauts, after docking, you can still communicate with such devices or with such modules, and you don't need to change completely the configuration of the network. And this synchronization can be achieved in the application we already developed in two ways. So here are two examples. So one, if you are using the real-time operating system which supports partitioning, like RX 653, then it's actually possible to use the extension to the driver, to the board, to the end system called TTE, which does the, let's say, the synchronization of the major frames, which is used for starting of different partitions on the real-time operating system, which is synchronized with the network time, and it means all the partitions and then all the applications will start synchronous to the network time, the major time frame. This can be used also to synchronize applications using the CFS middleware. So if the scheduler of CFS is synchronized to this, then basically also the applications running in CFS can be synchronized to the underlying network. Second option is to use, if this is not the 653 operating system, to use interrupts if this is enabled in the real-time operating system, to synchronize the execution or start of the execution of application using some of the interrupts that are provided by this TTE controller. So it can start, for example, with the interrupt which signalizes the start of the cluster cycle or integration cycle. So basically the periods in which the scheduled traffic repeats again and again. Well, so to provide a summary, I already explained so how TTE Ethernet can be used, let's say, to in a beneficial way to optimize the usage of resources, to optimize the runtime of the application. So not waiting for the data for a long time, but just be aligned with reception time, and also then to send the traffic to other system according to the schedule. So the determinism of such communication is, of course, the key. And also, TTE Ethernet includes a lot of, let's say, mechanism which increase the reliability of the whole network. Here, a short overview how the TTE currently is used on the Lunar Gateway, so on the modules currently in the development or already has been flown. So if I just start with the first, so Orion and including then the European service module. So the first two, and I think everyone in this room has followed the successful Artemis 1 mission at the end of the last year. Both of them have already used the TTE Ethernet technology developed some years ago at TTTech. This technology was not implemented in the TTTech products yet, so it was still the avionics which was at that time developed by Honeywell. But all other modules now in development for Gateway from PPE, Halo, International Habitat, and also Canada ARM already includes products from TTTech. I explained a few minutes ago. So some of them integrates the boards, some of them integrates them in the boxes, combined with flight computers. So basically SP0 computers. Some of them also integrate the controller itself in the smaller modules where it's more beneficial to interconnect some unit just using the controller, not using the cards in the boxes. And all of them running very similar software structures I showed on the previous slide. What is also important part of the development of such big network is the tooling. So here we provide the tools that are used to schedule the whole network in the modules, between the modules, but also to verify that the configuration of the network and its implementation in the configuration files for single devices are conformed. So basically verification tools to check the network configuration and the network and the device configuration files that are then uploaded to the devices in the respective module. So with this, I can close my presentation. Thank you very much, and I'm being here to take your questions.